Hello and welcome to a short video detailing what naive-based classifiers are, how they work, and how you may consider implementing them given the different types of data science or machine learning problems that you may encounter. So the first thing up is that to give a point of reference recently coming off of linear classifiers, what you should know about naive-based classifiers coming in is that you can gain some speed enhancements in their training, but at the same time, you do lose a little bit of generalization performance with your trained model. And you'll understand this a little bit as we go through here, but the main reason why that you'll see these performance changes is that naive Bayes is generally based on probabilistic models. And so your predictions, your model is created based off of probabilities, meaning that your reference points are relative to the actual data, as opposed to the hard concrete data that you're using to create your linear classifiers. So there are three major types that I want to highlight here. The first one is a Gaussian naive Bayes classifier. This is used primarily for data that is continuous. So if you have large numbers, decimals, take for example heights or amounts of water, for example, these are continuous data points. And so the Gaussian naive Bayes classifier is typically the go-to for this type of data. Bernoulli is essentially for binary data, yes or no, positive or negative, 1 or 0. If that's the type of data that you're working with, Bernoulli is probably the one that you want to try out first. And the third one is multinomial, which is typically for integer counts. For example, if you wanted to look at the number of times the word free comes up in an email, right? If you wanted to make a classifier that could detect spam emails, then you want to count the number of times free appears versus the number of times you hear manager or Saturday in the emails. So I'll briefly talk about how each of those works with very simple examples. So Bernoulli, the one I can probably talk about the easiest. Again, this is for binary data. So essentially, the calculations are made based off the likelihood on a per feature basis. And so you can understand that. I have a quick example drawn up here. You have three students, 1, 2, 3, and we want to know what influenced their results on an exam that they took recently. Right, so you can see over here, we have the first student passed, the second student also passed, but the third student did not pass. So, and the way you can understand this is by looking at, okay, we want to know based off of whether or not they studied, whether or not they did the homework, and whether or not they visited the teacher during office hours to talk about their subjects. And when we're talking naive Bayes, we're talking about probabilistic models here. And so we're going to look at things like, did they pass, right? Given that a student passed the test, what is the likelihood that they studied? What is the likelihood that they did the homework? What is the likelihood that they went to office hours? And so just one quick example here. Well, we see two students passed the test, okay? So out of those two students, in other words, given that they pass, what is the likelihood that they studied? Okay, well, of these two students, we can see that only one of them studied. The other one did not study. So we could say, given that they passed, there is a 50% chance that they studied. And the same thing for homework here. There is a 50% chance that they did the homework. For the office hours, however, there is a 100% chance that they went to office hours. And so in that case, office hours is going to be, or the attendance of office hours is going to be a strong influencer for whether or not a student passed the test. Right? That's sort of how that classification works in this sense. Talking about multinomial, so before we go there, remember Bernoulli is basically calculated likelihood on a per feature basis. And again, the data is these yes or no's or ones and zeros. The multinomial is calculated factoring in the mean of the different counts. So earlier I mentioned if you wanted to make a spam email classifier, you look at the number of counts that certain words have in your data set of example emails. And so a spam email might have some words at a higher frequency compared to a typical normal email. For example, the word free. A spam email will try to lure you in with these buzzwords that are likely to excite you and make you want to click on these links that are going to not really do anything good for you. So we take the word free, for example. Let's say there's 100 words in an average email, whether it's spam or not. Okay, and in a spam email, the word free comes up 30% of the time. You see the word free 30 times out of 100 in a spam email. Whereas in a regular email, the word free occurs 2% of the time. You see the word free 2 times out of the 100 words in an email. So you can see the probability of the word free is higher in a spam email compared to a non-spam email. And so if we, instead of just taking the number 100 for the number of words in the email, every email is a little bit different. They have more words, less words, and different kinds of vocabularies and whatnot. And so given a data set of emails, we can see the average number of times the word free occurs, right? That would be the mean in this case. You would use the word free, use other words that spam emails are likely to have, or punctuation mistakes and grammar errors and whatnot. You can look at the likelihood of that in your data set of emails and use that to classify whether you have a spam email or a non-spam email. Gaussian, remember this is based off of continuous data usually. It's similar to multinomial in the sense that the mean is also calculated, but because the data is continuous, the standard deviation is also factored in as well. And so if you want to take an example, look at the average height of somebody. If the average person is 1.5 meters tall, and in your collection of people, you can have a standard deviation calculated based off of the heights of everybody in your data set. And you could essentially form a Gaussian distribution, which if I find a little bit of room, if you haven't seen one before, it's generally a bell-shaped curve. And although it's not perfectly centered, your bell-shaped curve is, the shape of it is defined by your mean, which is typically at the middle here. We use a mu, Greek letter to connotate that. And the spread is typically defined by your standard deviation. And so, the likelihood that someone's height, let's do a little different color here for a quick second. The likelihood that someone's height is within this area is a lot higher than someone's height is going to be in these outer areas. And you can see that actually already with this graph, because this orange area, this region right here, takes up a lot more space than these smaller purple regions. And so if you have a given person, anyone just walks up, there's a much bigger chance that their height is going to be in this region as opposed to these other regions as well. Okay, so those are the three major types: Bernoulli, multinomial, and Gaussian. And a little bit of quick notes here just to wrap up. Multinomial and Bernoulli, if you're using these in programming languages or doing them by hand, there is an alpha parameter that's used as a means of smoothing. It's not a highly influential parameter or hyperparameter that you have in your model, but rather just something that can smooth out these probabilities so that they're not as rough. It's very similar to regularization in your linear models. The effect of regularization or this smoothing parameter is less significant with larger data sets, right? So if you're working with a smaller amount of data set, a number of data points that is probably smaller than you would prefer, then you can use this smoothing parameter to give minor tweaks and adjustments to your model once you've trained it. A second point here, Gaussian is often used for higher dimensional data. Just because of the complexity of Gaussian, given your mean and standard deviation, as well as the fact that your data points are continuous, the model complexity becomes a lot more significant. And so when you want to be working with higher dimensional data that has a larger number of features, not a crazy amount, but just more than 1, 2, 3 features, that's where Gaussian is really going to stand out. And lastly, Naive Bayes is a good baseline model. This is because there's more complex machine learning and deep learning algorithms that we're going to get to in later videos. But alongside linear classifiers, the Naive Bayes is a good one that you can start off with just to get a rough understanding of your data. Do you have enough points? Do you need to collect more information? Do you need a greater model complexity that can't be acquired through using probabilistic models or simple linear models? You may want to expand out into polynomial models or advanced types of machine learning classifiers, such as a decision tree, for example. So I encourage you to remember that going forward. Usually in your machine learning journey, when you're trying to solve a problem, you might try different types of algorithms just to see what can give you that best generalization performance, that classification accuracy. Naive Bayes can get you to a certain point, but think about the performance of this model once you actually train it, and think, can you figure out a way to enhance your performance, whether it's by modifying your existing model. Do you want to adjust this alpha smoothing parameter, or do you want to switch to a more complex, a more reliable machine learning model? So with that said, thank you for tuning into this video. Hope you check out another one. But good luck to you in your studies. Take care.